Okay, this is Giancoli Physics AP Edition, 7th edition. We're in Chapter 10, Fluids. We're working on problem number 16. Go ahead and dive in. The problem reads, determine the total force and absolute pressure on the bottom of a swimming pool. It is 28 meters by 8.5 meters, whose uniform depth is 1.8 meters. And then part B, what will be the pressure against the side of the pool near the bottom? Now, this is a slightly more advanced level 2 problem for this book. I reserve this problem for my honors and AP students. So go ahead and wrap your brain around this problem, pause the video, and see what you can come up with. Okay, so general problem solving strategies. Take note of the dimensions we're working with here. These are dimensions of a pool. Specifically, these are the horizontal dimensions. And I also have a vertical dimension. So it's going to be able to give us our volume and an area, depending on what part of the problem we're working on. They're asking us for the pressure, absolute pressure, and total force. These are all questions at the bottom of the pool. And then I also want to know the pressure against the side of the pool near the bottom. So we're going to take all those in turn. Another problem solving strategy is draw a picture. So I'm going to draw a picture here so I know what we're working with. As you all know, I'm a fantastic artist. Go ahead and sketch that out. Our pool is 28 meters, one of the horizontal dimensions. We have 8.5 meters along another dimension, and then our height or depth is 1.8 meters. That's what we'll be working with. To determine the total force on the bottom of the pool, it's tempting here to simply use density and the volume of the pool to calculate the force of gravity on this volume and use that to determine the total force. What's a little bit subtle about this problem and why I don't use this for my standard students is they're asking you for the absolute pressure and the total force. What's missing here, or maybe a little more subtle, is the fact you have air pressure pushing down on all of this, and that total force on the bottom of the pool is going to be due to a combination of this volume of water pressing down due to the force of gravity, which is valid, but you're also going to have that pressure from the atmospheric pressure pushing down transmitting through there also, so you have to add those both up. So we're going to go ahead and account for both of those and make that first calculated. It's actually easier to calculate the pressure first and then use that number to calculate the total force. So if we go reference our fluids related equations, we have these to work with. We're looking at the bottom of the pool here. The absolute pressure they're looking for at the bottom, as we discussed, is going to be a combination of the pressure due to the water plus the pressure due to the atmosphere. So we're going to have to add those two together. For the water itself, we have our equation over here. We're calculating the pressure due to a column of water. So it gives our absolute pressure at the bottom. Now, in using the force equation up here, once I know the pressure, I can calculate the force just by multiplying by the area. Again, I need to account for both of these pressure contributors in order to get that total force. So I'm going to go ahead and calculate the absolute pressure first using this equation. And then I'll use that quantity when I calculate the total force using my pressure equation. Let's go ahead and see if we have everything we need. We have the density of water, we have acceleration due to gravity on Earth, we have the height of the pool, the 1.8 meters, and we've got atmospheric pressure. I just need to make sure I put this all in compatible units. We should be good to go here. Density of water is 10 to the third kilograms per cubic meter. You can find that in a density table or search it up on the internet. 9.8 meters per second squared, our acceleration due to gravity. The height of our pool, 1.8 meters. Now, atmospheric pressure is 1 atmosphere, weirdly enough. But since these are all SI units, I want to use the SI version of atmospheric pressure, which again, you can find it in a table, 10.2 for Giancoli text, or search on the internet. 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. We're going to add that on. This is 10 to the 3rd. That'll make it 10 to the 4th. That's going to double it, so 2 times 10 to the 4th. We should expect an impact on this pressure over here. Oddly enough, the majority of the pressure here is still due to the atmosphere. So just realize this is going to have an impact here in the pressure in this decimal place here. So we expect 1.2-ish when we're done. Go ahead and pick up your calculator, see what you get. And your calculator should have told you a number in the vicinity of 1.18940 times 10 to the 5th, as expected. It did impact us at about 0.2 here on our 10 to the 5th. And again, that's pascals. Now, for the purposes of answering this question of absolute pressure, we're going to round to an appropriate number of significant figures, which looks like 2 is our restricting value here. But I want to save this number in my calculator, because when I use this number later for my force calculation, I'm going to want all the digits there and not have it rounded. So our absolute pressure here is approximately 1.2 times 10 to the 5th pascals. That answers part of our question. The other part of the question is the total force. Now that I know the total pressure at the bottom, I can use our pressure definition equation over here. Pressure is force per unit area. I know the pressure now that I've calculated. I'm looking for the force. The area I can get easily from these dimensions. Let's just go ahead and rearrange. I'll substitute the area on the fly as we go. But my force is going to be my pressure times my area. I'm going to go ahead and start substituting my numbers. Again, I don't want this 1.2 number. I want the full 1.18940 number for my pressure. And for my area, I'm just going to do my length times my width calculation. That's 28 meters and 8.5 meters. Which is the area of the surface of the pool. It's 1.2 times 10 to the 5th. 25 times 8 roughly would be 200. So let's just call that roughly 200. That should give us 10 to the 7th and double it to maybe 2-ish, a little more than 2. That should give the ballpark number that you should end up with here. So go ahead and pick up your calculator and see what it tells you. And your calculator should have told you something in the vicinity of 2.831 times 10 to the 7th as expected, so that's in the ballpark. And again, we're using SI units of pascals here, which is Newton per square meter, times a couple of meters, which can leave you with newtons. And that should be the total force at the bottom of the total force exerted by all that water and the atmosphere combined. Now, as far as calculating the last portion here, the pressure against the side of the pool near the bottom, we don't have to overthink this. We know that pressure is distributed evenly throughout a fluid. That's Pascal's principle. So because we're talking about the side of the pool, but near the bottom, translate that as at the bottom, the pressure is going to be the same as pressure on the bottom, which is going to be this pressure here, 1.2 times 10 to the 5th pascals. So we're done with this problem. Moving on to the next.